Good morning, good afternoon, good evening to our ever loyal Geek Speak audience of attendees. We welcome you to the last Geek Speak of 2022. And we're looking forward to spending a fun 60 minutes with you this afternoon or this morning or this evening, no matter where you're coming from. As always, I'm Matt Burns, Technical Marketing Manager here at Samtech. So welcome to our Geek Speak. And I'm joined by my esteemed colleague, Scott McMurrow, who's coming to us from warmer parts of the world. Scott, how's it going today?
It's good today. It's a good day. It's 84 degrees in beautiful Puerto Aventuras, Mexico, and looking forward to the last Geek Speak of the year.
Excellent. Please share that warm weather with the rest of us that are in cold weather locations. So we really appreciate
Yeah, I've been watching the snow coming through the country, and I'm glad I'm not up in Maine right now.
Fair enough. So we know you send warm thoughts to all of us.
Absolutely.
In any case, before we start talking about the weather too much, Scott, can you introduce our presenter today?
Yes, our presenter today is Michael Griese, and he is the manager of our RF signal integrity and connector design group. And he's got a wonderful presentation on the impacts of solder reflow on high bandwidth RF connectors. And if any of you have ever had to work with solder reflow connectors at high bandwidth for RF, it's actually really hard to make them stick on the board. And I'm sure he's going to talk about that and what happens when the solder is not reflowed correctly. Just a word of reminder. We do not use the chat window. For questions and answers, we use the question and answer window that says Q&A. Post your questions, and we'll either answer them offline or in the background or live on the presentation. I'll present them to Michael. And with that, and then at the end, we'll have a word about what's to come. So with that, I'll turn it over to Mike.
All right. Well, hello, everyone. Thanks, Scott, for the introduction, and thanks to all of you for joining us. Again, my name is Michael Griese, and Scott already introduced the topic, the name of the topic, so I'll press on with that. I guess maybe some additional information to kick us off there. Within this topic or within today's presentation, we're going to be taking a look at some of the lessons learned. That's going to include an example that I'll go through with some root cause investigations and then some incremental modifications that were made to improve the performance and ultimately increase the usable bandwidth. And as Scott pointed out, yes, this is a tricky topic. So that's why I think we thought it would be good to share with everyone. One last thing I want to mention while I'm on this opening slide here is that you also see Chris Shelley's name on here. He was the electrical expert behind today's presentation, but he is busy enjoying the retired life. So I'll be the one to share the lessons that Chris learned and ultimately help Samtech provide some better products for our customers. So I just wanted to open with a thank you to Chris in the off chance he's listening. And lastly, I should mention that Chris was also working really closely with the Interconnect Processing Group here at Samtech, or IPG for short. And they were doing the actual soldering and the processing of these boards. So IPG, they were the solder experts, where Chris was the electrical expert. And I just wanted to mention them up front. You'll probably hear some more about IPG as I go through, but I wanted to mention them because they could be a resource for you as well. So with that, I'll stop chatting to the front screen and move into our presentation. Just a little bit of background before we get to the example. From a design perspective, we're often starting out with some ideal assumptions. So here we have an image of just some generic component, and it's soldered very nicely in place. And I do believe that this is a fair assumption to make at the beginning, since this is ultimately the goal, right? To have something soldered nicely and properly in place. However, truth be told, that we're being a bit optimistic here. Some may say we're looking through rosy-colored lenses. So, everything looks great at this point. That is, until we actually apply the solder. So here I'm pointing out a worst case scenario where this component is lifted off the pad. It doesn't even make contact, right? So the good news is it's at least easy to catch in a visual inspection, but the unfortunate thing, at least for this example starting this webinar, is it doesn't really exemplify the more nuanced challenge that's going to be presented by the solder itself when the component or the connector is even fully mounted on the board. So just because it looks good doesn't necessarily mean it's going to perform well. That's the point that I'm trying to make. So nonetheless, even with that catastrophic example, that is in fact the starting point for today's presentation. So we'll get into the details, of course, as I go through the example, but the goal here for the presentation will be for us to get from something like this to something more like this, not just soldered nicely on the board, but also performing up into high frequencies. And just one quick slide on Samtec, and the off chance that you're not familiar with us. Samtec does offer a large catalog of electrical connector and interconnect products. It's including a wide variety of high-speed and precision RF solutions, such things as high-speed, high-density backplanes and arrays, some high-speed edge card and mezzanine solutions, flyover technology, some high-performance optics. Our focus for today is precision RF connectors and cable assemblies, as well as some newer developments with innovative packaging solutions and waveguide technologies. But again, today's focus is on that sort of center bottom blue circle, precision RF. So we will zoom in and focus on that. And in particular, we're going to look at our push-on line of connectors. And at the bottom left of all these different options is an SMPM surface mount. That is going to be our example for today. So just setting up the example and what we're going to try and accomplish. Here's that SMPM surface mount down at the bottom left that is mounted and soldered oh so nicely on this PCB, at least in the image. But what we really want to do is sort of lift that off, both literally and figuratively, of the board and look underneath the connector and, or I should say, between the connector and the PCB itself at that solder joint. So, all right, let's jump into the example with the initial design here. So I think this probably goes back a couple of years now, but the initial approach to designing this connector was a more conventional approach at the time. Traditional two-piece contact is inside of there with horizontal and vertical components. And you can see, at least in this image, sort of a rectangular shaped pin that's protruding out of the escape. And the initial goal, as it says at the bottom left there, was to target 40 gigahertz. And hey, it's good to have targets, but at the time it was looking like, at least through simulation, that 25 gigahertz may have been the limit of that initial design. Unfortunately, out of the gate, the first trick was not getting the performance necessarily, but just getting the connector to mount onto the board. And I think that's where Scott opened us up with the trickiness of getting these things to stick in the first place. So here again, we see that catastrophic tombstoning effect, as I mentioned earlier. Some might call this an inline series capacitor. I think most of us would probably call this just an open circuit. But again, we're starting with the worst case here, but with some work on the processing side, they were able to get some good connections on a few samples, as we'll see on the next slide. But it's also important to note some of the proposed probable causes at the time that we're showing in the bottom right there in bullet points. So the first one was the gold plating. Started with a relatively thick gold plating on the body of these connectors. One of the things that's, I'll say separate from the gold plating for just a moment, but just in general, is that with these push-on connectors, you definitely want to have a mechanically strong bond of the connector onto the board, because there's some force associated with pushing that connector on and pulling that connector back off. But back to the gold plating, too much gold plating led to some voiding, which we're going to see later on, that had some impact on how this was being mounted in the performance. The second thing was the insulator thermal coefficient of expansion. So when thinking back to the two-piece contact construction that I mentioned earlier, the vertical piece has had a retention barb that displaced a portion of the insulator when it was inserted. And so that sort of material that was displaced combined with the thermal expansion of the material itself led to that insulator effectively pushing the connector off of the board. So if you'll have to imagine this, but imagine that insulator sort of expanding and pushing down onto the board and causing it to separate under reflow. And then that third point, the center contact barb, is related to the second point that I was just mentioning. So that just sort of added to the trouble of trying to get this connector to stay flat. But as mentioned, there were a handful of connectors that were fully mounted onto the board, not quite as bad as we're seeing here in this image. So they were able to get some measurements out of that, or out of those, which looked about like this. So here we're looking at measured data up to 25 gigahertz. Now, the good news was that the correlation between the simulated model and the measured performance was pretty good. So we knew we had a good model, but the obvious bad news was that the model was correct. So we were limited to about 25 gigahertz as opposed to the more optimistic 40 gigahertz target that we started with. So this was definitely a good start nonetheless. There were lessons learned along the way, and one of which was maybe we need to take a different approach to the design of this connector. So that was the first attempt that led to some redesign on the connector for the second attempt. So this right now is just a reminder of what we saw previously. This is the initial design with the probable concerns on the bottom left now, just reminding us this is what it looked like. This is what we believe the problems were. And then this was the new contact, that's sort of a one-for-one, what changes were made to address those 3 points. So the first change was thinner gold plating on the body to, again, try to help with that soldering process and not leave to gaps or voiding between the connector and the board. Higher temp insulators and a swept contact, again, to try and keep the entire connector sort of flat onto the board during the soldering process. And something just to mention that I don't think is stated on this slide is that again, targets are good. So we tried for 40 gigahertz last time and didn't make it. Let's try for 55 gigahertz. So that was the new target for the changes in the design. Did a lot more testing for processing up front. It wasn't perfect out of the gate, but between the previous lessons that were learned and the modifications to the design, they were able to get some good results mechanically, and they looked good, at least visually. They were on the board, they were mounting the way that they should. So again, now I'm kind of going to, before I showed you the worst case, this is more of the best case, at least in these samples. But the point is that there were a lot of improvements made between the design and the lessons learned previously. So, okay, that's how it looked. How did it perform? And the answer was much, much better. So had we had kept that 40 gigahertz target, we'd have blown that out of the water, because here we saw 45 gigahertz. And this is why you always need to move that goalpost. If you have a chance to do better, give it a shot. So, it was encouraging to see the improvements and the lessons that were learned along the way. Definitely is what led to this success. But with that said, 55 gig was not quite, we weren't quite there. And one of the biggest issues that should be jumping out on this slide is not necessarily the worst case, but the fact that there was a lot of variation once we got past about 45 gigahertz. So, we had good performance. This was definitely a success. But now the question becomes, what's going on above 45 gigahertz? Is there anything we can do about it? And the other thing, if you look closely on the last slide, is that there was some encouraging news. If I take a look at the sort of best performance from a broadband perspective, it showed that 55 gigahertz was possible. So the hope was maybe if we can figure out what's going on with this variation above 45 gigahertz, that 55 gigahertz, that target is well within reach. So what can we do about that? And the last thing before I get into sort of the troubleshooting and investigation, we'll look at one other area that was looked at that sort of led the investigation, which was these are the same measured, or I should say samples that were measured in the frequency domain previously, but this is just looking at the TDR time domain. And we're going through the connector around 0 picoseconds here, and we're seeing this capacitive dip that was not expected in the design, somewhere around 50, 55 picoseconds or so. And so, okay, it wasn't what was expected, which means we're scratching our head saying, what is going on? The other thing that's interesting about this dip is not just that that low impedance was unexpected, but that we do see some variation across this. So, you know, easily 2 ohms of variation, maybe a little bit more than that. And the other thing that's interesting about this is, you know, we believe that this was still in the connector at the time. And so on the connector manufacturing, there's some pretty tight tolerances. So again, what is going on? What is causing this dip? But also what is causing this variation? And is there any relationship to the variation we're seeing in the frequency domain? Okay, so we have a saying in our group, the best way to find a solution is to first understand the problem. So with that in mind, that is exactly what Chris sought out to do. We'll take a look at that. So the first thing was just a visual inspection here. So again, I showed you sort of a best case scenario previously in an image, but somewhere in the middle of the pack, or I should say maybe the typical or more average type sample looks something like this. And what was noted, if you look around, and hopefully you guys can see my cursor, but if you look around the outside of the body, you can see quite a bit of solder that's wicking up the sides. Also, it was noted that there was some excessive solder on the connector pin as well. But just kind of thinking about the excessive solder around the body and trying to relate that back to the previous slide on the variation of impedance, this is not inside of the connector. It's not in the transmission line. So in a way, this really shouldn't be directly impacting us. However, it had us thinking, okay, if the external solder looks like this, what does it look like between the connector and the board? What is actually happening inside? Is it possible that this solder could be going in places that we didn't know and therefore kind of didn't really want them to, because it's not what we had predicted? So with that in mind, the next thing we did was start to investigate. So here we're looking at some experiments that were ran taking just the connector itself and soldering that body onto the board and then pull it off. Now, one thing that you should be able to see is some of the voids that I was mentioning earlier when I was talking about the gold plating. But that's not really the focus on this slide. The focus on this slide is if you look at that bottom rounded sort of keyhole section, the question that I posed on the last slide was, is that solder going somewhere else that we didn't anticipate? And here was our first evidence that sure enough, that may be happening. So there was some solder found pooling around that inner edge of the pad. And so we tried to isolate this one observation and run some simulations to see what this might do to our performance, and particularly we're looking at the impedance in this case. So a ring of solder was added to that same area, and the volume was varied, which was effectively changing the distance between the conductive material through that solder joint to the center contact inside of the connector itself. And so the question was, you know, what kind of impact might this have on our impedance? So on the right-hand side, it's the same image we saw previously, but we're just pointing out what was being varied in the model. So again, increasing the volume of the solder and effectively increasing the coupling. And if there was some impact, the expectation would be that adding solder is going to increase the coupling between the contact and the body, which should effectively reduce or drop the impedance through that section. And while that was in fact observed, and it makes complete sense that it would drop the impedance as the volume increased, and again that means that the distance is shortening between those two conducting bodies. The impact was pretty minimal. So you know, maybe a small impact on the overall performance, but this is not what seemed to be causing that large dip that we saw in measurement. And plus, while I'm not showing the measured data on this slide that we saw earlier, the location of this variation was a bit further back in the connector. So the next idea was to then move that solder pooling forward along the bottom edge of the connector, moving it towards the exit. So something like this. And hopefully you're noticing on the right-hand side, we have the same connector, we have that same pooling of solder around the backside or the keyhole, but we've added some solder along the exit and varied that volume as well to see, okay, what happens here. And if I'm looking at my impedance results here, things are starting to get interesting. We're seeing a bigger impact. The thing that we're not calling out the step size in here because it's not too important as far as the numbers are concerned, but the step size of the simulation as far as the distance is concerned were linear steps, but it was just interesting that the response was nonlinear. Not to make too big of a deal out of it, it was just an interesting observation. But again, even though things were getting interesting, the impact that was observed, it still wasn't quite right. It wasn't as large in magnitude, and it wasn't quite in the right location. It still seemed to be a little bit further back, again, as compared to measurement. So again, maybe some impact overall, but didn't seem to be the root cause of what we saw. Okay, so we changed our tactic. Before we were just looking at the body, and we ran some more experiments to look at the problem a little bit differently. And so this time we had the full connector soldered onto the board, pulled that off just like we did previously, but this time we were able to see a new interesting feature. And it's kind of hard to see in this image, I apologize. So that's why there's that black bracket trying to point out what is interesting here. But towards the top of that image is the pad that was pulled off from the PCB. Of course, you have the connector towards the bottom, and you have that contact that's coming from the center of the connector, sweeping around onto the board, making contact to the pad, and there is a little bit of solder that is starting to creep from beyond the pad and into that connector. Okay, that's interesting, but the story gets worse because actually there was a ton of variation. In fact, none of the samples really looked the same. And so we saw solder wicking a little bit all the way to a lot, and of course, everything in between. And so this was an interesting feature. It also had a lot of variation. So again, we went back to simulation to see, could this be the culprit? Could this be what's causing our issue? So some solder was added in the simulation and varied along the length of that, that contact up into the connector. And these are what the results look like through simulation. And here, things not only got interesting, we started to get pretty excited because this is starting to vary in the right magnitude and the right location, the impedance that we were seeing in measurement. And so, you know, again, this was significant. It was in the right location. And we also were seeing variation inside of our soldering physically. And so this gave us some pretty good confidence that, hey, maybe we're on to something here. And at this point, it makes sense to take the one trace that looked pretty close to what we remembered in our measurements, overlay that with our measurements. And I would say this is a pretty good correlation between the model and our measurements. So again, this gave some confidence that, hey, maybe we're on to something. Maybe this has something to do with why we're seeing the variation in performance. The last correlation that we want to do before we proceed is to take a look at that in the frequency domain. And when we look at that data, again, we see some pretty good correlation there. We weren't necessarily trying to capture all the variation through the simulation here, but there was almost certainly an impact to all of the variations that we looked at, but the primary meaning the keyhole and along the length, right? So everything that we ran in simulation had an impact, but really the primary contributor appeared to be that solder wicking up that center contact. And again, not only did this show the strongest correlation, it was also the observation with the most variation from sample to sample that we saw visually, meaning that that solder was landing in different locations from sample to sample. And so this suggested that, hey, maybe this variation in performance could be caused by that variation in the solder wicking up the center contact pin. Okay, so that was sort of our experiments and troubleshooting, root cause analyses, using simulation to try and sniff out where the problem might occur. So, okay, what do we do with this information? Well, from here, there are three things that we can look at changing. We can make changes to the connector, we can make changes to the PCB, and we can also make changes to the reflow process itself. So, of course, we explored all three of those options, and I'll run through those quickly here. The first one, the first option, I should say, again, was could we make some changes to the connector? And one change that was made here was adding a chamfer to that inside edge, with the idea being that hopefully this could help minimize that solder pooling that we saw around the back and the exit on the boards, on the samples that we saw. And to give a little bit more detail, there is some open area, some volume that the solder can sort of flow into, and also a longer distance to travel before it starts to get into an area that could be impacting our performance. So we just wanted to give it room to kind of move around and do whatever the solder wanted to do without having a negative impact on the transmission line. And here's the results of that. It's a little bit hard for me to resolve, but I'll try to walk through this verbally here. On the right-hand side, you're seeing the center contact coming out of the connector and sweeping up towards the top right of the image. And then sort of to the left of that, or behind of that, you see where the solder is going along that chamfered edge. So in other words, this was evidence that the chamfer was doing what it was intended to do. It was giving the solder somewhere to flow without pulling up inside of that sort of sharp corner that existed before. And again, this is just a different angle that shows, we'll highlight here, that you can see where that solder was, again, able to kind of move around, do what it wanted to do, but not encroach into the transmission line that would have some negative impact on performance. Okay, so that was the first change specific to the connector option. The second option that I mentioned was a change on the PCB. So thinking about that solder wicking up the center contact, was there anything that we could do to that? The previous was, what can we do about the solder pooling around the inside edge? Here we're saying, what can we do about the solder that's wicking up that center contact? And the idea here was to kind of lean into it a little bit. Let's let the solder wick up the pin, but let's not let it go wherever it wants. Let's try to give it a specific location every time, with the idea being that if we could reduce the variation between our samples, then that might help us address the variation we saw in performance. And so what we're looking at here is, again, the connector was soldered to the board, and here we've pulled off the pad, and you can see a little bit of that pad extending back underneath the connector, where we're calling here, it's the solder control tail. And so essentially this is just a small little extra piece of pad that goes intentionally inside and underneath of the connector to say, hey, solder, you can flow here, but this is it. This is where you have to stop. And that worked pretty well. There was still variation. It didn't work perfectly, but it did at least reduce the variation, and that was the goal. So here we saw a success from that perspective as well. Okay, so far we've changed the connector, we've changed the PCB. That leaves us with the process itself. And really this came from IPG's expertise in trying to figure out what's the best way to solder this onto the board. The first thing that they did was look at and make some modifications to the thermal profile. So previously they were starting on the left-hand side, what they consider to be an aggressive thermal profile, with a peak temperature of 254 degrees Celsius and 82 seconds for a reflow time. They modified that to the right-hand side, which they would consider a moderate thermal profile, had a lower peak temperature of 244, a lower reflow time of 62 seconds. But the other thing that's a little bit more subtle is comparing, if you look closely at the slopes and the shapes of those curves as the temperature is ramping up from the aggressive to the moderate profile, the moderate profile sort of ramps up a little bit quicker in the beginning, slows down, and really the goal here is to get the ambient temperature to reach some equilibrium. So modifying this profile, the hope and the intent was that it would be more consistent across parts, it meaning the equilibrium, reaching equilibrium. But there were some other things that they changed in addition to the thermal profile. So some other changes, I'll just walk through these at the top table here, was changing the solder paste from a water soluble to a no clean, changing the reflow environment from a nitrogen to an air environment, changing the stencil thickness from 5 thousandths to 4. And this one is effectively reducing the volume of solder that you have there, right? So if we have less volume, then hopefully it won't start to move around in more and more places that we don't really want it to go. There's a little bit of a trade-off here. You can't go too thin or you lose the whole advantage of it being a mechanical bond to that board. And so again, you get into problems with, maybe it doesn't even solder on in the first place, to maybe it solders on to begin with, but you start pushing and pulling on connectors and it pops off. So you can't go too thin, but nonetheless, 4 mil is where they landed. And we talked about the reflow process on the previous slide. And the other thing is on the bottom left, the stencil itself. So there is a stencil aperture that has this sort of channel that runs through it. And they played around with that, ended up landing on a sweet spot, but that was slightly wider from where they began. This channel does a couple of things. One, the channel, there's not any volume of solder there. So again, not only did we reduce the stencil thickness, but there's just less surface area where that solder is going to be applied and therefore less overall volume. But the second thing that this does is it provides a channel for that solder to off gas. And so the hope there was to, again, minimize those voids that were between the connector and the board. And so we want a strong mechanical connection to the board, but we don't want that solder to go anywhere near a transmission line, or at least if it is, we want to know where it's going and anticipate it, right? And I'm trying to think if there's any other points I was supposed to make about processing, because this is out of my realm of expertise, but I think that's all I have to say on the IPG side of things. So the question then becomes, we made those 3 changes, right? We changed the connector, we changed the board, and IPG helped modify and improve the reflow process itself, which leaves us with, how did it go? And we're going to start with the impedance profile first, since that's what we were using in our troubleshooting. We are back to measured data. So this is real data, not simulated data. And the first thing to note here in this data is the impedance variation was reduced. So this was good news. This was one of our primary goals in some of these changes that we made, was to reduce the variation from sample to sample. So that was good news. The second thing to note, though, is that the capacitive dip was successfully raised, but a little bit too much. So unfortunately, if our target is in the center of this plot at 50 ohms, we went from this large capacitive dip to being a little bit more of an inductive spike. But again, it was a little bit more controlled. And I would say that the good news that comes out of that is we were clearly playing around with the right parameters, because we achieved the objective of raising that that was previously capacitive, so raising that dip in our TDR. And the other thing to mention here is that while we are a little bit high in the impedance here, it's a bit of a smoother transition throughout the entire TDR, and so that's going to have some positive impacts on reflections, and there the hope being that our VISWAR is going to improve overall. So, okay, this is the time domain. This is what we accomplished with the changes. What does that mean for our performance in the frequency domain? And here it is. The result was, in fact, an improvement in bandwidth performance. So there's an exclamation mark there. Hopefully, the excitement is coming through in my voice. This was good news. We hit the goal, if you remember, of 55 gigahertz that we were targeting. There was still some variation that was above 55 gigahertz, as you see on the right-hand side there. And just to remind everyone, previously we were seeing bandwidth of about 45 gigahertz before that variation kicked in, just beyond that, and was sort of limiting our performance to 55 gig. And so, again, 55 gigahertz, we met that target. Beyond that, there was still some variation. It was definitely reduced, but the question then becomes, could we do better? And there's some hope in there. I won't spend long on this particular diamond in the rough or cherry-picked data point, but it's nice to see something like that because it gives us hope, it gives us confidence that there is room for improvement in the future. But with that said, I wanted to also throw up the performance requirements here. So in the meantime, and this is where the story sort of ends from a performance point of view, but if we compare the results we see on this slide to the performance specs that we were trying to meet, they really look great all the way up through 55 gigahertz. There's a ton of margin. So not only was it a success, it was really, I think, an overwhelming success when you put these specs on the same plot there. So with that concluding, sort of what happened and how we ended up with the connector and changes and the performance. This is the actual connector that we went through in the example. This is just some information that's pulled from our website. So if you're interested in this in particular, you're welcome to go take a look here. And these are these specs that I was referencing on the previous slide. And so again, this is the actual connector that we saw throughout the entire presentation, or I should say the end result of what we saw throughout the presentation. The changes that were wrapped up inside of the connector that we went through, of course, if you purchase and you're using this connector, that's just part of the connector itself. But that leaves the question of, okay, if we need to design the PCB, how can we be successful? So one other thing that I just wanted to share is we didn't talk about the details of the stack up or the launch throughout this presentation, but this is information that is available and we do share with our customers to just kind of quickly run through the stack up that we're seeing here that we used throughout this example, or maybe it wasn't throughout, but certainly towards the end. You see that it was a core out construction. It was a 4-layer board that was used. MT40 was used here for the dielectric. It's a good material, but not the most expensive. So a little bit of thought went into trying to keep a balance between performance and cost. But again, this information is available to customers, just for reference design and if it could be of value to you guys. In addition to that, we could share footprint information in like a PDF image format. Now the footprint could vary a bit from the prints because the reference design, really, which is what we were focusing on here, that's going to include a lot more details that are specific to the stack up that was used, right? So again, the details on the geometry are specific to this stack up that was used in our reference design. But beyond that, we could share with you the individual layer details, images, Gerbers, different formats, just let us know. But, breaking this up in this slide, the solder mask, what that first layer is going to look like. Of course, any of the VIA details would be included. Layer 2 in this particular launch has some anti-pag cutouts to handle the impedance as the connector is transitioning into the board. And then layer 3 was a reference plane right at the launch, but layer 2 effectively becomes a reference plane inside of the transmission line. And the last thing, I don't have a slide for IPG, but that would be the third thing that you might be wondering from your side. So, okay, we have the connector. There's some information to help with the launch, but what about the processing, which was a big point of today's presentation? Just to note that customers can also reach out to the IPG, again, that's the Interconnect Processing Group at Samtech, so they can be a resource for customers as well. And if you're trying to get this launch or some kind of launch to work, There are resources. We have these resources. And the last point to make here is that if you're trying to get a launch to work on your own stack up and you're looking for help, then I would encourage you to reach out to customer support online. Samtech offers support to our customers for customer launch designs on their boards, right? You might have a different stack up and therefore your design, your launch may be different. So either way, if you need help getting performance out of a Samtech connector, we're easy to talk with here at Samtech. We want to help you be successful. So please don't hesitate to reach out to the customer support team if we can be of support to you and help you be successful with our products. So that brings me to the end of the detailed dive on the SMPM example. I do want to note, however, that these challenges are not specific and they're not unique to just this SMPM surface mount example that we went through. As Scott said at the beginning, pretty much anytime you're soldering a connector onto a PCB, we need to overcome these types of challenges. So the last section, I just wanted to share some examples of additional tools and techniques that we use at Samtech to help us get a better idea at addressing these challenges. As well as sharing some examples of some other connectors that went through a similar iterative process to improve the processing as well, and ultimately improve the performance and consistency. So jump into that. Excuse me. So starting with some tools and techniques that we have at Samtech that we didn't see in the rest of the presentation. We have some imaging options that are available to us. So here we're seeing an example of an X-ray. We also have some CT scan capability. And this gives us a chance to not just see inside of connectors, see inside of boards, but this is nice because it's a non-destructive test method, right? And so we can start to get an idea of what everything looks like on the inside, as opposed to just some of the visual inspections that we saw earlier in the example. Another thing is similar to what we saw, but a little bit different, which is soldering things onto a board and then removing them to inspect and see what happened in the soldering process. Where this is a little bit different from what we saw in the presentation is this is just a top layer that has the footprint itself. So it doesn't include all of the SI details, vias, launch, etc. This is just the top layer for experiments to see, what happens. Now, there are some differences in what happens between a simple board and a full SI board because of the content, the volume of metal, how thick that stack up is, what each layer contains, right? So the thermal profile of the board is a little bit different, but nonetheless, this is a faster process that we can run through and start to get some ideas that, as we're doing a design, where do we think there's going to be a problem and what can we do about it? I mentioned destructive processes. So mechanical cross-sectioning is definitely a destructive process. There's no going back, but this is great because we see some additional insight that we wouldn't see out of an X-ray or a CT. One thing that I find particularly interesting in this image, it's a little bit hard to see, and again, hopefully you can see my cursor, but if we know this top layer is about 2 mils of copper, this is a solder float that the entire connector is riding on. And this was a helpful piece of information that tells us that, hey, I can eyeball it and say that's about 1 mil worth of solder that the connector is floating on top of. And so, how much solder goes between a connector and a board, where that solder goes, as we saw through some of the troubleshooting, is helpful information when we're doing our modeling, so we can try to anticipate that and either do something to prevent that from happening or do something that's going to counteract that in our design and say, okay, we know the solder is going to go here. What can we do in our design to anticipate that? And the last thing on this slide I won't talk too much about, but just an example of the SI boards. And this is effectively the example of what we were using in the testing throughout the example. And so building SI boards that we can test and see what is the actual performance going to look like is obviously a very valuable tool to us. And another tool, so everything that I showed previously was on physical, either imaging or measurements. Another thing that we're starting to look at is modeling the solder reflow. So anytime I've referenced simulation up to this point, I've always been talking about electromagnetic simulation. But another tool that we have available to us that our mechanical and fluids experts at Samtech are helping us with is looking at modeling this solder process itself. This is something that's kind of new to us. We haven't really figured out all the details, but we are getting some promising results from this that are showing us, hey, maybe we can use this in future designs and start to predict what's going to happen with the solder. And so just to note that the example I'm showing here, it is in fact the same connector and details that we were showing in the example above. So you can start to see the impact of that stencil and that channel that I was mentioning. It had that channel width of A in one of the previous slides. And so you can see where the solder paste is applied. Now, the engineer running these simulations, they're starting with just the CAD itself. So they're starting with the mechanical CAD or the model of the connector. Obviously, the material characteristics. They're starting with the same layout CAD that we're using for our SIG design and for fabrication, but they're also using the stencil itself, and they can apply, I'm putting this in air quotes, they can apply the solder paste into that stencil, so that solder is then part of the simulation itself. And so this is sort of the starting point at the top left. And then as they run the simulation, you can start to see this solder start to move around, right, as it would. And so it's not just a single simulation, it's applying different conditions that might impact the way that the solder is going to reflow. And so, you know, changing the wetting angle, for example, of the contact seems to have a pretty big impact in how well or not well, maybe well is the wrong word because we don't want it to happen, but whether or not that solder goes up that center contact and how far it goes up. The other thing that is the note there on the bottom of the image, it is maybe more for me because it didn't make a lot of sense. When I first looked at this, I thought, why is there not a volume of solder? The solder volume is there. By default, the visualization just shows the surfaces. I think that we have since learned how to include that visually, but just note that what you're seeing at the top right is that the solder did flow outside of those channels and is filling in the voids between basically what we see as the surfaces of where that solder is flowing to in this image. And then the last thing, which I think is probably the most important, at least with regards to what we talked about today, is we do see that solder pooling in the back of the keyhole along the exit in the edges. I shouldn't say pooling, that's probably wrong because this includes the chamfer, but we do see the movement just like we saw in the images after we made the modifications. And we also see that that solder wicking up the center contact. To be honest with you, I don't know if the solder control tail is in these examples or not. But the point really here is just that this is another tool that we're exploring and trying to figure out, just like we predict what's going to happen electrically, could we try to get a feel for what's going to happen with the solder? And that might give us things like, you know, hey, should we, if we do put a chamfer on, number one, should we? Number two, how large should that chamfer be and how large is large enough? And likewise with the solder control tail, does it make sense to put it there? Does it look like it's going to do what we think it's going to do? How wide should that tail be? How long should that tail be, right? So this could help us optimize this before we go into test, right? Save us a lot of time and a lot of money doing the building and the testing. Okay, so those are all the tools. The last part I want to run through quickly are just a couple of other examples, and I think that'll leave us about 10 or so minutes for questions, if there are some. But I mentioned that, you know, this is not, these problems are not unique to just the one connector we saw in the example. So here's a couple other examples. Here's a ganged SMPM edge mount. At the top left, we see an actual image of some of the solder, and won't go into too much detail other than just to point out at the bottom here, this is the TDR profile. And let's see, the red trace here should be J4, so that's the bottom pin, and the purple trace is J5, so that should be the top pin. And if you look closely, J5 has quite a bit more solder on it than J4. And so going from our previous logic that we saw, we know that if we have more solder volume, that's going to bring our contact, in this case, it's more on the contact than the body, but anything that is going to bring that conductive surface closer to coupling, That's a capacitive load. And so we should expect to see on J5 a more capacitive launch and J4 a more inductive launch. That's exactly what we see. And the other thing to note is, look, this is on a ganged connector. So we're seeing variation. This is one solid piece that went through the exact same process, right? Because it's just one component, one connector that's on one board. And so even from channel to channel, we are seeing variation. And so again, some similar iterative process to try and resolve that problem, but just sharing this as an example of things that can go wrong. Here we're looking at an edge mount example. And so here we're seeing things that didn't go so great. And so you can see, again, a lot of wicking up along the sides. It's a little bit hard to see in these images, but in sort of the bottom center, you can see that the solder was flowing in different amounts and different volumes, leading to maybe different types of gaps and voiding underneath the connector, just on the same one connector, not even necessarily from sample to sample. And ignoring the details in this particular example, again, you go through an iterative process, you find ways to make improvements, and in the other end, we end up with not just improvements to the soldering, but the implication is that improvements in performance. And then one last slide on some examples. We'll look at some through-hole examples, because these are a little bit fun to look at. You have these extra ground legs that you got to figure out how to solder on properly. And so the first example here is showing, you see a lot of void between that center, sorry, not the center contact, but these ground legs. You see a lot of void between those posts and the board where it's supposed to be soldered to. Are the holes too big? I don't know, maybe is there not enough solder? Maybe, I'm sure, again, there's some different changes we can make to improve that. So if that first example was voiding or not enough solder, this next example is too much solder. If you look at sort of the bottom left leg, I think it's a little bit easier to see. You see a large accumulation of solder here, as well as between the connector and the board. And you also see some variation from leg to leg where there's not quite as much. So we're seeing issues with accumulation as well as variation. Similarly, you could have things just short out. So here we have the center contact that is shorting out to a ground leg. Here we have a combination of not just not enough solder, but also some lifting off of the contact. So similar to that tombstoning we saw. And here's another tombstoning example where everything's still in contact, so it wasn't necessarily catastrophic. There's probably still a connection, electrical connection there, but nonetheless, that is not desirable and has an impact on the SI moving through this gap. So those are all things that's gone wrong through a lot of hard work, a lot of iterative process, like we saw with the SI engineers as well as the IPG engineers. You get to something that looks good. So with that, I think I didn't leave us 10 minutes. Let me run through the takeaways. First and foremost, as hopefully you saw throughout this presentation, solder reflow plays an important role in the success and performance of high bandwidth RF connectors. So hopefully that was obvious throughout the presentation. In this example, to better control the solder reflow, we made changes to everything we could. We made changes to the connector, we made changes to the board, and we made changes to the process to improve our performance and yield. And in the end, the result of all this hard work was these changes did in fact improve the product. It did improve the performance. And so this is the connector you can see on our website today. And lastly, while we focused in on one specific example, the SMPM surface mount, these challenges are not unique to just that one connector. This is a challenge, as Scott said, when you're trying to solder a connector on the board, it can be a little bit tricky. So with that, hopefully I left some time for some questions. If not, you can always, or if you don't get your question through, you can contact the RF team, rfgroup@samtech.com. You can contact our IPG team, ipg@samtech.com. And of course, you can always contact customer support on our website. Okay, how are we doing on questions? That's all I have.
Well, it turns out we don't have any questions right now. So open it up for questions if anybody has some. We did have one person that was asking about placing RF connectors through essentially a doer connection, but that's sort of off. That's an offline discussion that we have to have. Anybody?
Okay.
Well, if not, thank you all for coming. I'll turn it back to Matt, who will close. Oh, we do have a question. Wait a minute. Interesting. All right, we have a comment. Interesting study. Thanks for sharing. Happy holidays. That's from Bert Simonovich. Matt,
Thanks,
can you
Bert.
go ahead and close us out?
Yeah, thanks again to all of our presenters. Michael, great job. Would like to give Chris Shelley a shout out if he's listening in. So thanks for all that hard work. Great presentation. I think we all benefited from it. Scott, it's been a fun time always co-hosting with you over the last 12 months. Look forward to doing it again next year as well. We've gotten some questions via email. What are our plans for 23? We are planning on going back to a monthly cadence next year, starting in January. We're working on finalizing our schedule. So we'll look to have that posted on our landing page, samtech.com/geekspeak, before the end of the year. We are going to kick off 2023 with a preview of some of the presentations that the Samtech team will be given at DesignCon. So we invite all of you to look forward to registering for that. And hopefully that'll be a nice teaser for what no doubt will be another successful DesignCon event at the end of January. With that, thanks again for everyone for making our program so successful. Without our listeners, we wouldn't be able to present GeekSpeak. So we thank you, and we look forward to being with you all again next year. Our presentations, as always, and the recording will be posted on samtech.com/geekspeak within the next 24 hours. If you have any questions for the GeekSpeak team, please reach out via email at geekspeak@samtech.com. And all technical questions can be submitted to our SI team, such as Michael and Scott at sig@samtech.com. With that, we bid everyone a good afternoon, and we'll look forward to talking with you all next year. Thanks again.